Slow zoom out of Earth. Suspenseful music builds gravity. It's the most familiar force in your life, pulling you toward the ground, holding your feet to the floor, guiding rivers downhill, and keeping our planet orbiting the sun. But don't let its everyday appearance fool you. Gravity is a silent tyrant, an invisible dictator of the cosmos, and when you follow its influence beyond Earth out into the vast black ocean of space, you realize that gravity isn't gentle at all. It's not mild, it's terrifying. Gravity doesn't just keep planets in place. It warps time, bends light, and crushes stars into singularities so dense they tear the fabric of space itself. Gravity is the reason black holes exist, the reason time moves slower near massive objects, the reason galaxies spin and form structure. Without gravity, there would be no stars, no planets, no us. But with it comes the potential for cosmic destruction on a scale no human can comprehend. Let's break it down. Simulation of space-time fabric. Warping around a planet. According to Einstein's theory of general relativity, gravity isn't a force in the traditional sense. It's a curvature of space-time. Imagine space-time as a giant trampoline. Place a bowling ball in the center. This represents a massive object, like a planet or a star. Now roll a marble across the surface. The marble curves inward not because of some invisible string but because the surface itself is distorted. Now, imagine a star 10 times the mass of our sun, or a black hole with a mass of 4 million suns packed into a single point. That trampoline isn't just dented, it's punctured, and anything nearby is doomed to spiral in. Time-lapse of the Earth orbiting the sun. You may think Earth's orbit is a simple path, but it's actually the result of space itself being bent around the sun's mass. We're not circling it like a racetrack, we're falling into the sun, constantly missing it because of our sideways speed. Gravity is balance, a perfect tug-of-war between motion and attraction. But when the mass gets bigger, that balance becomes chaos, and nowhere is gravity more dangerous than near a black hole. Scene: star being devoured by a black hole. As a massive star reaches the end of its life, it explodes in a supernova, ejecting its outer layers into space. What's left behind is a collapsing core. If the mass is great enough, gravity wins. It crushes the star into an infinitesimal point of singularity surrounded by the event horizon, the point of no return. This is gravity's ultimate form. Nothing, not even light, can escape it. And what's worse? Time near the event horizon moves slower. Much slower. In fact, if you hover just above the edge of a black hole, 1 minute for you might be hundreds of years for the rest of the universe. That's not science fiction, that's physics. This effect is called gravitational time dilation, and it's been proven by satellites orbiting Earth. Even our GPS systems need to account for it. But near ultra-massive objects, this phenomenon gets extreme. Gravity doesn't just shape space, it twists time into a knot. Deep space galaxies orbiting each other. Cosmic ballet. On the grand scale of the cosmos, gravity forms galaxies. Billions of stars pulled together by mutual attraction. But galaxies aren't stationary. They're spinning, colliding, merging. These are gravitational giants battling each other for billions of years. And yet, there's a mystery. Based on visible matter alone, galaxies shouldn't be able to hold together. They're spinning too fast. Stars should be flung out like mud from a spinning tire. But something is holding them in place. An invisible grip, a gravitational force we cannot see. Zoom into dark space. Dark matter, whispered faintly. This mystery leads to one of the most chilling possibilities in modern physics. Dark matter. We'll explore it in the next chapter. But for now, understand this gravity may not even be finished revealing what it truly is. Because despite how central gravity is to everything, we still don't fully understand it. It's the only fundamental force that doesn't fit within quantum mechanics. Unlike electromagnetism or the nuclear forces, gravity resists unification with the rest of physics. The more we try to probe its secrets, the more elusive it becomes, like a cosmic riddle. Some scientists believe gravity may be an emergent property, not a fundamental force at all. Others suspect it may connect us to hidden dimensions, or that it leaks into our universe from parallel realities. All of this is theoretical, yes, but remember, so was black hole theory. Until we saw one. Scene: 2019, real image of May 7 black hole appears. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. It confirmed Einstein's theories and visualized gravity's ultimate triumph. But it also raised more questions. How does information survive in a black hole? Can gravity and quantum mechanics ever be merged into a single theory of everything? What happens at the center of a singularity? No one knows. But here's what we do know. Gravity is both creator and destroyer. It birthed the stars from clouds of gas. It keeps planets in stable orbits for life to evolve, but push it too far, and it becomes a devouring monster. It can stretch time, collapse dimensions, and silence light itself. Zooming into a rotating black hole, eerie music fades, and his is just the beginning. Gravity is the most familiar force, but also the most deceptive. What lies beyond its extreme? What happens when gravity merges with other terrifying forces? In the next chapter, we'll go deeper into the abyss, where gravity is king and reality unravels. Black holes, where reality ends. Slow motion of a dying star, imploding, deep bass rumble builds. They are the ultimate enigma of the universe. Black holes, born from destruction, powered by gravity, and cloaked in shadows so deep that not even light can escape. When a black hole forms, it doesn't just kill a star, it rewrites the laws of physics. It creates a region in space where time, matter, and even reality itself cease to behave as we know them. If gravity is the master of the universe, black holes are its executioners. But what exactly are they? A black hole begins when a massive star far heavier than our sun runs out of fuel. For millions of years, nuclear fusion kept the star alive, pushing outward against the crushing force of gravity. But once that fuel is gone, gravity takes over. The star collapses inward with unimaginable force. If it's massive enough, it doesn't stop at forming a neutron star. It continues falling until all its mass is crushed into a single point of infinite density, the singularity. Surrounding this singularity is the event horizon boundary, so absolute that nothing, not even light, can cross it and return. Cross the event horizon, and you've exited the known universe. Simulation of a spaceship approaching a black hole. Imagine watching someone fall into a black hole. From your perspective, you'd see them slow down, stretch, and eventually freeze at the edge. They would appear to stop moving, as if time itself had paused. But to them, they'd fall straight through in seconds, feeling no different at first until they were torn apart by the black hole's tidal forces. This is known as spaghettification, a real, horrifying process, where the gravity at your feet is so much stronger than at your head that your body is stretched into a thin strand of atoms. It's not science fiction. It's pure, deadly physics. Deep space. Supermassive black holes at galactic centers. Black holes aren't rare. In fact, they may be everywhere. At the center of nearly every galaxy lies a supermassive black hole, millions to billions of times more massive than our sun. Ours, called Sagittarius A, sits quietly at the heart of the Milky Way. It's 4 million solar masses. Silent, but not harmless. These giants didn't just appear. They likely formed when the universe was young, swallowing gas, stars, and even other black holes to grow into the behemoths they are now. They shape galaxy formation itself. Without them, galaxies like ours might not even exist. But not all black holes are quiet. Some are monsters actively feeding on matter, creating powerful accretion disks that glow brighter than entire galaxies. These are called quasar sand. They can shoot jets of energy thousands of light years into space. Quasar erupting with energy, bright jets streaming from galactic core. This leads us to one of the most terrifying truths. Black holes don't just destroy, they can also become engines blasting energy, warping space, and shaping the evolution of everything around them. But black holes also carry a mystery so profound, it could change our understanding of the universe forever. What happens to the information inside a black hole? In physics, information can't be destroyed. But black holes seem to destroy it. If you throw a book, a star, or a person into a black hole, where does that information go? Is it trapped forever? Is it smeared across the event horizon, as some theories suggest? Or is it lost, breaking the most sacred laws of quantum mechanics? This is known as the black hole information paradox, and it's one of the greatest unsolved puzzles in science. Stephen Hawking once proposed that black holes evaporate over time via a process called Hawking radiation. Tiny particles escape the black hole's edge, slowly bleeding away its mass over billions of years. If true, a black hole could eventually vanish, leaving behind nothing. But if it disappears, what happens to everything it consumed? Does that information re-emerge? Or is it lost forever, erasing causality and breaking the foundation of quantum physics? Some scientists now believe the information is somehow encoded in the Hawking radiation. Others think black holes may lead to new dimensions or even other universes. Which brings us to the boldest theory of all, seen. Wormhole visual, time and space folding. What if black holes are gateways? Some physicists theorize that the center of a black hole may connect to something called a white holean, opposite entity that spits matter out instead of sucking it in. Together, they could form a wormhole tunnel through space-time itself. If real, this could allow for instantaneous travel between distant points in the universe, or even time travel. But there's a catch. The center of a black hole is a place where the equations of general relativity break down. It's where our understanding of space, time, matter, and energy completely fails. We don't know what happens beyond the singularity. We can't know. It's a literal edge of reality. Pullback shot from a black hole to a galaxy. Black holes are not just astrophysical objects. They are cosmic prisons of information, destroyers of light, warpers of time, and perhaps bridges to the unknown. They represent the raw, untamed power of gravity, taken to its most violent extreme. And we're only beginning to observe their true nature. Thanks to telescopes like the James Webb and the Event Horizon Telescope, we're peering deeper into these monsters than ever before, but what we see only deepens the mystery. Black hole consuming a star. Fade to black. They lurk in the shadows of galaxies. Some feed, others sleep, but all wait with patience that outlives stars. We call them black holes. But the truth is, they are the gatekeepers of the universe's deepest secrets. In the next chapter, we turn to something equally terrifying. Objects so dense, so deadly, that just a spoonful of their matter would weigh as much as Mount Everest. Prepare for Chapter 3, Neutron Stars, the Cosmic Time Bombs.